Yeah, welcome to the latest HACC Tech Talk in our 2024 series. My name is Naveen Purushottam from the AMD University program, and I'm very pleased to be able to welcome our two speakers for today. Our first speaker for today is Dr. Viveka Konandur Rajanna, who is an assistant professor in the Department of Electronic Systems Engineering at Indian Institute of Science, Bangalore. His research interests include ultra-low power VLSI circuits, in-memory computing, memory design, low-power human-sensor interface, and secure on-chip computing. Today, he will present on the topic energy-efficient computation for machine learning workloads.
Thanks, Naveen. Thanks for the kind introduction. Thank you all of you for joining, and I welcome you to this talk, which addresses the energy efficiency challenges of computation, specifically targeting machine learning workloads. Right. So a brief introduction about myself. I'm Viveka, like Naveen introduced. I'm an assistant professor currently at IISc Bangalore. Before this, I was a postdoctoral researcher at National University of Singapore. And before that, I've had some academic and industry experience. I've done chip tape outs over a wide range of technologies, ranging from the ancient 180 nanometer all the way down to 22 nanometer in academia, which means that the tape out involves the entire flow. And we're getting into today's talk. This is the motivation for the talk. We have seen the evolution of computing paradigms over the years. On the x-axis is the year, and on the y-axis is the number of shipments, the parts in millions. The late 80s and the early 90s had the demand for computation primarily driven by personal computers. This was then taken over in the 2000s, early 2000s, by mobile phones. We then evolved to having computing requirements from smartphones, which saturated somewhere around 2015. And off late, over the last 3 to 5 years, we have seen a boom in the computation requirements thanks to the advancements made in artificial intelligence and specifically machine learning algorithms. The data center this have increased their computation workloads exponentially over a short period of time, and this translates to computation workloads. Seen here, the famous Moore's graph. On the x-axis again is the year. On the y-axis in the curve shown in blue is the number of transistors or the number of parameters in log scale. So we know famously that the number of transistors have increased by almost doubling every year. But since the advent of AlexNet and how the ML community has boomed, seen here in green, the increase in number of parameters of these networks, which were initially focused on solving image processing or video processing applications, the number of parameters there increased by roughly 2.5 times every year. Then came the age of transformer-based large language models, where we saw that this increase in rate changed from 2.5 all the way to 18 times per year. This number of parameters in each of these models or algorithms also translates to compute requirements. So this next slide shows the number of training computations or the number of computations required to train these huge networks. During the image processing time frame, where we had AlexNet and the VGGs and ResNets, the increase in number of training computations required for training was around 2.5 times every year. But with the LNMs and the transformer-based networks, this again changed to around 18 times per year. This is all the BERTs and the chat GPTs and so on. How does this translate into training time? So BERT, which is a network by Google, is estimated to have around 109 million parameters, which took around 1.9 petaflop days to train. Then came ChatGPT a short time after this, where the number of parameters increased to 175 billion, right? And it took 3,600 petaflop days to train, with an estimated cost of around $4.6 million. At this rate of increase, it is estimated by 2030, around 850 terawatt hours of power is required just to supply data centers in the US alone. This amounts to around 20% of all power generated in the US. This is a significant portion of power going dedicated just to data centers. On the other end of spectrum is the hardware or the latest efficient hardware in doing these computations. A plot here shows the energy efficiency, which is typically measured in teraops per watt. Another way of saying how many tera operations you can do if I give you 1 watt of power. And on the y-axis is area efficiency, or this can be read as cost. So we see that the latest and greatest or the most efficient hardwares have an energy efficiency of around 330 terawatt per watt. This means that by 2030, we'll need more power to supply only data centers, and even all the power generated in the US will not be sufficient. The challenge of today is thus of energy efficiency and to build more efficient hardware so that we can meet the demand of computation arising out of these emerging applications. Towards bridging this energy efficiency gap and addressing challenges of energy efficiency at various stages in the compute tool chain, an overview of the research that I have conducted over the years is presented today. We start off with memories, specifically in SRAMs, and how the energy efficiency can be improved there. We then to look at optimizing the optimizing the energy, moving data from one point to another point using on-chip links within a chip. Sensors and interfacing with the outside world is a requirement for most systems today. So we look at one project which optimized the energy efficiency in interfacing to sensors outside of your chip. Ensuring that your computation platform is secure is another important challenge. And the next topic we look at ensuring we look at a design that is able to detect if your chip is under attack. And lastly, we look at a conventional sort of neural network accelerator that can be used in a generic way to optimize energy efficiency of most state-of-the-art neural networks. So starting with memories, back during my PhD days, I designed what is called UDVS memory, or ultra dynamic voltage scalable memories. These are memories that can operate over a wide range of voltages. In this work, implemented in a very ancient 130 nanometer technology, we demonstrated an SRAM that can operate from 1.2 volts all the way down to 190 millivolts in a completely integrated manner. So reads were working down to 190 millivolts. The highlight of this work was that we were able to achieve this wide range of operating voltages while being the fastest across this wide range of voltages. In each of my work, I also highlight the places at which this work was published to showcase the impact that this work has had. We also compare our work with other state-of-the-art works to show the comparative, to highlight the contributions made with each of these work. We then move on to in-memory computing to address the challenge of moving data between memory and processor, which is proposed, which is the conventional von Neumann way of computing. In-memory proposes that we do computation at the same place that we store data. So in-memory computing paradigm basically combines data storage with computation to achieve extremely high energy efficiencies. In this specific case, use SRAMs, where data is given on word lines and data 1 or activations are given on word lines, and weights or input 2 is stored inside bit cells. And at every bit cell, we do an AND operation or a single bit multiply operations. We then we add the result of multiple multiplications on a highly capacitive bitline. We then use some sort of analog to digital conversion to translate this analog computed value into digital domain. In-memory computing offers extremely high energy efficiencies, but trades off some accuracy. This specific in-memory computing chip implemented in TSMC 28 nanometer was targeted towards data buffering and inference applications, where you have a steady stream of incoming video data, which has to be buffered, but also some amount of inference needs to be run on this incoming video stream. The highlight of this work is that it proposed an SRAM cell, which increased the number of transistors in every cell by 3, while maintaining the symmetry of the SRAM cell. Conventional SRAM cells only have the ability to draw charge from the bitline, but this SRAM cell has the ability to both add and subtract charge from the bitline. Using a configurable ADC whose resolution can be adjusted to meet the requirement of different machine learning algorithms, we can change the energy efficiency and increase it to up to thousands of teraops per watt if the application can support it. We demonstrated in-memory computing macro using 3 popular neural networks and showed that the accuracy degradation by running these algorithms on our SRAM was well in line with what others have proposed in literature. Using this SRAM, we were able to achieve best-in-class energy and area efficiency. Continuing on the theme of SRAMs, another requirement of most systems is to generate security perimeters. These are basically unique keys or random keys that need to be generated for encryption and decryption algorithms. PUFs or physically unclonable functions generate a unique ID, which means that every time PUF is asked, queried for a number, it returns with the same unique number. TRNGs or truly random number generators give you a truly random number for every query. Both this was integrated within an SRAM itself, which was the first demonstration of this kind. This implementation was done in a mostly digital manner, which brings all the benefits of scalability with it. Using this, we had a highly area efficient design, and the design is also more secure because it was integrated within the memory, making it more resistant to attacks. This is also demonstrated on a 28 nanometer silicon die. Moving on from memories to moving data on chip from one point to another point. So optimizing the energy used in moving data from one point to another point in typically large chips that have on-chip networks is also very important. A large amount of energy, depending on who you ask, is spent in moving data itself. And one of the best ways known to optimize energy in on-chip links is to optimize or use low swing links, optimize the swing. This work, we utilize two main factors. We realize that not all bits going on these links have equal importance. The MSBs, for example, have a higher impact on the overall accuracy of the system compared to least significant bits. On the other hand, we also observed that on the thousands of links that are there on typically large chips today, not all links tend to be very bad, and so it's not ideal that we margin regular links for these worst case links. In this work, the chip starts by characterizing the links that are being fabricated in the chip, and we then prioritize to send the most important bits on the best links available. Combining the microarchitectural ideas in this chip, we were able to achieve energy efficiencies in 28 nanometer comparable to that of the energy efficiency in a 16 nanometer chip. This chip in 16 nanometer used circuit techniques, which can also be combined with architecture techniques in 28 nanometer or the work proposed by us to get even higher energy efficiencies. This work was demonstrated across 3,200 links of 4 different types of transceivers across 20 different devices, showing the robustness of the techniques that we proposed here. We then move on to a sensor interface work. The challenge in this project was to build an electronic skin interface, and the main challenge here is that the density of skin-like sensor array causes challenges with respect to signal and power distribution. Here, we encode signals from multiple receptors, in this case 80 receptors, onto a single wire using a spread spectrum encoding scheme. This way of encoding has several temporal and spatial sparsities inbuilt into it. This chip utilizes or exploits all the sparsities to give you best-in-class energy and area efficiency, while being mostly digital design, bringing again all the benefits of scalability with it. This was a cost-sensitive application, which is why this was implemented in a 40 nanometer test chip, which is shown here. Ensuring that your chip is robust to attacks is another important challenge. So side channel attack is a way of attacking your chip by observing the current consumed, the current profile of your chip. Just by monitoring the current waveforms of your chip, attacker is able to decipher secret keys stored within the chip. So it's important to make our chip robust against such attacks. In this chip, we basically built an on-chip spectrum analyzer that analyzes the impedance profile of the power network of your chip. Once a chip is implemented in its final application, this on-chip spectrum analyzer analyzes the impedance profile shown in green under normal circumstances. Then, if an attacker puts the current probe into the power network to monitor your current waveform, that causes a change in the current impedance profile, shown here in red. These curves here in this graph are measured curves which show a baseline operation in green and attack scenario in red. Not only were we able to detect attacks, but we were able to do it with a very high degree of confidence. The statistics of these measurements are also shown, which shown that our ability to detect attacks is very robust, even including statistics, right? We're able to detect this with a higher degree of accuracy. The impedance profile is, we can generate a profile of impedance from low frequencies all the way up to 2 gigahertz. And the area overhead of making this chip robust to attacks is comparable to just the area of a couple of pads. This low area, almost fully digital idea is able to make your chip robust against side channel attacks. The next work is on actually building a DNN accelerator that can be employed across a wide range of applications. This utilizes what is called as a dyadic digital pulse modulation, which is basically a pulse density based modulation scheme compared to the conventional pulse width based modulation scheme. By converting the encoding scheme to a density based encoding scheme, the conventional operations which are multiply and accumulate, which dominate machine learning algorithm computations, can now be translated to just a simple counter, which means the number of logic gates used to implement 8-bit MAC is reduced by around 5x. Right? This is a fully digital implementation, but employs approximate computing. Thankfully, most machine learning algorithms are robust to errors. Right? Using the error tolerance of these applications in a conventional 14 nanometer design, we were able to achieve energy and area efficiencies comparable to the latest technologies in 5 and 12 nanometer designs. A little brief about the work done at IISc. In addition to having a beautiful wide campus at the heart of Bangalore, IISc offers students and collaborators the opportunity to pursue and interact with students pursuing PhDs, masters across various streams, contract positions, employees working under contractual, short-term and long-term contractual positions, and internships of various durations. So if you are interested in the work that we do, I encourage you to reach out and use opportunities to collaborate with IISc. Here is a quick view of various silicon demonstrations done by me over the years. These are just a highlight across the years, with me having contributed to many more projects across a wide range of technologies. A typical testing scenario is hectic and messy and looks something like this, but working with academia gives you the opportunity to work across the spectrum of a chip design, right from specification all the way to taping out your chip and measuring and characterizing results to demonstrate the supremacy of your ideas. Thank you for giving me this opportunity, Naveen and others at AMD for having me. Thank you, the audience, for making time and listening to me. I am open to questions now, and feel free to reach out to me at these email IDs or have a look at our lab website to understand more about the work we do.
Yeah, thanks, Viveka. Thanks for the great talk. Just one question from me. So, in terms of like very good research on in-memory computing and the chips that you have, sent for fabrication. So the question I had was kind of, where do you see, or how much do you think, or how soon do you think that such in-memory computing could be coming in mainstream accelerators like GPUs and FPGAs for deep learning use?
A good question. Actually, if you see the evolution of in-memory computing, it started off being approximate computing. Over time, over the last year, it has now moved on to full accuracy computations. We have now started seeing works on what we say floating point operations also. Earlier it was 6-point only, but now they even support floating point. Looking at commercial applications, over the last couple of years, there are actually commercial designs that use in-memory computing, commercially available chips that you can buy off the shelf that use in-memory computing. So while the approximate computing is also translating into commercial spaces, with the advent of being able to do floating point operations, I'm sure big computing platforms, people who do the GPUs and server class systems, will also see utilization of in-memory computing, because you can also run training, which is what these server class machines are generally used to do. So hopefully in the next 5 years, we should see in-memory computing in GPUs and servers as well.